In this lesson, we will begin an introduction to limits. This is an exciting lesson because in earlier lessons and earlier studies, we're concerned with situations that don't involve change. They're static situations. For example, how much would 100 items cost? Or how wide is an arc 10 meters from the ground? And other situations like that are considered static situations. But in calculus, we look at situations that involve change. Here are some examples. How fast is the car moving after 20 seconds? That involves a situation that is changing. At what rate is the population growing? Or what is the rate of change of profit when sales reach $1,000? These are examples of situations that involve change. These are examples of problems that we look at in calculus. Solving each of these problems requires a derivative. The definition of the derivative involves the idea of a limit of a function. Now, this is very important. The limit concept is what distinguishes calculus from other branches of mathematics, such as algebra and trigonometry. So, when you're studying algebra, when you're studying trigonometry, traditionally you do not study limits. So, this lesson is going to be a gateway, if you will, to your studies in calculus. So, this will be very exciting. To get us started, consider this rational function. F of x is equal to x squared minus 4 divided by x minus 2. Here is the graph for this function. Now, we did look and study rational functions, and we have actually looked at a function like this before. This function, f, is not defined at x equal to 2. Let me remind you that if x were 2, this denominator would be 2 minus 2, which would give us 0 in the denominator, and therefore making the function undefined. So this function is undefined at x equal to 2, which gives us a hole in the graph when x is 2. So this function would have a hole here. This is a point of discontinuity is what we would say. In earlier studies, we would factor the numerator as x plus 2 times x minus 2. Notice that the factors x minus 2 divide out, leaving you with this simpler expression, x plus 2. So the graph of f is basically the graph of this line whose slope is positive 1, whose y-intercept is positive 2. However, this line will have a hole when x is 2. And notice when you plug in x equal to 2, you get 2 plus 2, which is 4. So the hole is at 2, 4. Now, what I want to explain next is the idea of a limit. So if I consider what f of x is equal to as x values approach x equal to 2, that's considering what the limit is. So as x values get closer and closer to 2, as x values get closer and closer to 2, my function values are getting closer and closer to 4. And I can show you this way. As x values get closer and closer to 2, my function values are increasing, right? As x values increase toward 2, my function values are increasing, approaching the function value of 4, right? And the same thing is happening on the other side as well. If you allow x values to approach 2 on the right, your function values are approaching 4. One strategy is to make a table of values. And so what I am doing here is I'm allowing x values, which is this first row, to get really, really close to 2. So here it's 1.99. Let's get even closer to 2, 1.999. Of course, we can get even closer to 2, right? 1.9999, and you can get as close as you want. On the right-hand side, here we're getting closer to 2 from the right. So 2.01, 2.001, and of course we can get even closer, right? 2.0001, 2.00001, and I think you get the idea. We can get really infinitely close to 2. So here you can see that these x values are getting closer and closer, moving in on x equal to 2. And when you allow x to be 1.99, the function value is 3.99. When you allow, and again, you can just plug in these x values here to confirm that, right? Plug in x equal to 1.99, you'll get 1.99 plus 2, which is 3.99. If you let x be 1.999, the function value is 3.999, even closer to 4. If you let x be 2.01, the function value is 4.01. That's really close to 4. But if you let x get even closer to 2, 2.001, the function value is even closer to 4, 4.001. So looking at this table of values, one can conclude that as x values get closer and closer to 2, the values of f of x get closer and closer to 4. So we can see from both the graph here that it's still on the screen and from the table that we just looked at, we can see that as x values get closer and closer to 2, and notice that x values never actually equal 2 because the function's undefined at 2, the values of f of x get closer and closer to 4. So what we say is the limit of x squared minus 4 over x minus 2 as x approaches 2 equals 4. And this is the notation. The limit as x approaches 2 of this rational expression, x squared minus 4 over x minus 2, is equal to 4. Okay, so this here, this subscript, this is the value at which we are considering x values getting closer and closer to. 4 is the actual limit. Okay? Now, you and I are going to get awfully familiar with this limit notation here. And what I really want to highlight is, although the function f is not defined at x equal to 2, we can still consider the limit of this function as x approaches 2. Here is our definition for the limit of a function. This is very important. Let f be a function and let a and l be real numbers. So f is the function, a and l are real numbers. L is considered the limit of f of x as x approaches a. And this is how you write it. The limit of f of x as x approaches a, that is an arrow right there. The limit of f of x as x approaches a is or equals L. Okay, this value right here is A. This is the value that your x values are getting infinitely close to. This is your function, and this is the real number value that your function values are approaching. Now, this is true, so L is that limit of your function if the following two conditions are met. First, as x assumes values closer and closer but not equal to a on both sides of a, the corresponding values of f of x get closer and closer and perhaps equal to L. Okay. Now remember that the previous example that we saw, the function was not defined at x equal to 2. So x was not allowed to equal 2. So that's why it's saying x is assuming values closer and closer, but not equal to a, right? We don't necessarily need x to actually equal a, right? In the previous example, we did not need x to actually equal 2. We just needed x values to get infinitely close to 2. on both sides, by the way. Remember on the previous examples, we let x be, what was it, like 1.9 and then 1.99 and then 1.99. X values were getting closer and closer to 2 from the left. And then also x values approach 2 from the right. We said let x be 2.1 or 2.01 and then 2.001. And so we were closing in on x equal to 2 on both sides. That's what this is saying, on both sides of A. Number 2, the value of the function values can be made as close to L as desired by taking values of x arbitrarily close to A. So you can get closer and closer and closer to your limit L. All you got to do is allow x values to get closer and closer to A. Now, this is very important. The definition of a limit basically is describing how your function values are behaving, like what's happening to your function values as x gets near A. So you're looking at what is happening to your function values as your x values get closer and closer and closer to A. Now, and this is what I was saying earlier, this is not affected, right, by whether f of A is defined. In the previous example, once again, the function was not defined at x equal to 2, but we were still able to consider what the limit was as x values approached 2. So this is very important. This is going to be like the foundation upon which we build everything for our limits moving forward. All right, check this out. We want to find the limit of a polynomial function. So I have a polynomial function here of degree 2, so it's a quadratic. We want to find the limit of this quadratic polynomial function as x approaches 1. One thing we could do is get the graph of this function. We know it's going to be a parabola because it's quadratic. We know the parabola will be opening upward because the leading coefficient is 1. What else do we know? We know the y-intercept will be 4. Let's also find the vertex, and then we can just sketch the graph really quickly. I can use the vertex formula, negative b over 2a, to determine the vertex of this parabola. And again, I am not trying to get a very, very detailed graph. I'm just trying to get a sketch of the graph. So I think I know enough. It's opening upwards. I have the vertex here. I know the y-intercept. So let's go ahead and get sketch the graph of this parabola. All right, folks, I have a rough sketch of our function here. This was that vertex I found, which was 3/2, 7/4. Here's the y-intercept. So the question is, as x approaches 1 on both sides, okay, what are f of x values approaching? Again, as x approaches 1, what is happening to f of x? All right, so this is what I want you to see, and we can also get a table going if you'd like. I have to approach 1 from the left, so that's what I'm doing here. As I approach 1 from the left, my function values are behaving like this, are coming in that direction. And it looks as if, just like looking at the graph here, it looks as if it's approaching 2. But I need to confirm that. As I approach x equal to 1 from the right, my function values are also, it looks as if the function values are approaching 2. So as x approaches 1 from the left and from the right, it seems as if the function values are approaching 2. What we can do to confirm this is we can start plugging in some x values that are close to 1 from the left and close to 1 from the right, and then inspect their outputs. All right, so look at this. As I allow x values to approach 1, so this is from the left, okay, to the left of 1, I got 0.99. Notice that my function values are 2.11 and then 2.0101. As x approaches 1 from the left, my function values are approaching 2. Now, as I allow x values to approach 1 from the right, so first at 1.1 and then at 1.01, the function values are 1.91 and then 1.99. So as x values approach 1, my function values are approaching 2. So what we're going to say is from the graph and also from the table, as x approaches 1, f of x approaches 2. 2 is the limit. And this would be our notation. The limit of this quadratic function as x approaches 1 is 2. Now, what I want you to notice is that this is a polynomial function. Remember that polynomial function is continuous over its entire domain. And so we know that the limit of this polynomial function as x approaches 1 is going to be exactly equal to f of 1. If we were to just plug 1 in, 1 squared minus 3 times 1 plus 4, if you actually just plug 1 in, you will get 2. However, we cannot assume this to be true for all functions. But for polynomial functions, finding the limit of a polynomial function, all we really have to do is just take this value that your x values are approaching, plug it into your polynomial function, and that will be your limit. However, not all functions behaves like this because it's not every function that, some functions don't have a domain or are not continuous over its entire domain. For example, let's look at a piecewise function next. Let's go ahead and add this, before we move forward, let's add this to our notes. Kind of a summary of what I was mentioning earlier. Let me see if I can move all of this up just a little bit for better viewing. Here we go. The polynomial function given in this example is defined at x equal to 1. And the value of the limit happened to be f of 1. If we would have just plugged 1 into the function, we would have gotten the limit, because 1 squared minus 3 times 1 plus 4 is 2. That is to say, the limit of f of x as x approaches a will always equal f of a. Make sure you understand that, folks, that you can find a limit by just plugging a into your function. Just evaluate f of a, and that will be your limit. But that's only true for polynomial functions because they are continuous, okay? We're about to look at some other functions like a piecewise defined function, and things will be different. But if you're dealing with a polynomial function, the limit of that polynomial function as x approaches a is simply f of a. That's super helpful. Here we have a piecewise defined function. So they're asking us to find the limit of f of x as x approaches 3. And f of x is equal to 2x plus 1 for x values that are less than or equal to 3, or 4x minus 5 for x values that are greater than 3. And I want to make this look more like an x there. Let's get a graph and so that we can see what's going on. All right, so I got my plane going here, this x and y axis, and this is the point 3, 7. What I did is I plugged 3 into this piece. 2 times 3 is 6, 6 plus 1 is 7. So 3, 7, 3, 7, right? And what I'm going to do now is just from this point, and this is how I graph piecewise defined functions, this is a line, so this is mx plus b form. I'm going to move according to my slope. So my slope is 2. So what I'm going to do is I cannot go up 2 and to the right by 1. I cannot do that because this line is only defined for x values that are less than or equal to 3. So I need to go to the left. So I'm going to have to go down 2 and to the left by 1. Down 2 and to the left by 1. So if I go down 2 and to the left by 1, that leaves me to 2, 5. Right? If I go down 2 again and to the left by 1, then I'm at 1, 3. If I go down 2 and to the left by 1, I am at 0, 1, which is that y-intercept right there. So this, if I just connect the dots really quickly, this is the line for that first piece there, okay, for this piece. This piece starts this line starts for x values that are greater than 3. Because we can get infinitely close to 3, I'm going to go ahead and plug 3 in. 4 times 3 is 12, and 12 minus 5 is 7. So this line starts here as well, and then I'll just move according to my slope, which is up 4 and to the right by 1. Up 4 to the right by 1, that will put me at 4 comma 11, which is way up here, kind of off the graph. So I'm just going to do this, folks. So from here, it shoots up like that, up there somewhere. Okay? Now, here's the question, everyone. I trust that you're able to graph a piecewise defined function. This is something that we've done in earlier studies. The question here is, what is happening to your f of x values, your function values, as x gets infinitely close to 3? Now, I'm going to look at when x gets infinitely close to 3, look at here, gets infinitely close to 3 on the left-hand side, my function values are approaching what looks to be 7. Now let's check from the right. From the right, as x approaches 3 from the right, my function values are approaching 7 as well. So we can also use a table like we've done in the previous examples. The graph here shows that, and keep in mind, everyone, that this piecewise defined function is actually defined at 3. And so what we can say here is that the limit of f of x as x approaches 3 is 7. So let's practice our notation. So it's the limit of, and we can just say the limit of f of x, because f of x is actually defined up here, okay? So the limit of f of x as x approaches 3 is 7. That was cool. Let's look at another piecewise defined function. All right, this time we want to find the limit of our function as x approaches 2. And this is how our function is defined. Again, two linear pieces here, right? So both of these are lines. This is a line whose slope is 4, whose y-intercept is -5. This one is slope 3 and y-intercept -5 as well. But this first line is only defined for x values that are less than or equal to 2. This line is defined for x values that are greater, strictly greater than 2. All right, let's get the graph. So I would actually encourage you to pause this video here and graph this function on your own, and then play the video again, and let's see if your graph and my graph are the same. All right, folks, this is the graph that I got, and let me walk you through, just in case, how I achieve this. So I first started with this line here. I plugged 2 in. 4 times 2 is 8. 8 minus 5 is 3. So 2 comma 3 is this point here, folks, 2 comma 3. And what I did was I used my slope. My slope is 4, so I went down 4 and to the left by 1. I had to go down 4 and to the left by 1. I could not go up 4 and to the right by 1, because this line, again, is only defined for x values that are less than or equal to 2, okay? So I went down 4 and to the left by 1, got the secondary point, and then drew the line like that. For this piece here, I went ahead and plugged 2 in. 2 times 3 is 6, and 6 minus 5 is 1. So 2 comma 1. Open circle here, because this is a strict inequality, okay? So this line is not defined. This piece is not defined when x is 2, right? So that's an open circle. And then I just moved according to my slope, +3, and then to the right by 1. So when I go up 3 and to the right by 1, I end up at 3 comma 4, which is up here. So the line goes that way, okay? Now, here we go, folks. This is a very important example. We want to know what's happening to f of x, what's happening to my function values as x approaches 2, Okay, now watch this. As x approaches 2 from the left, actually let me do that a little better. As x approaches 2 from the left, my function values, watch this, my function values are approaching 3. Did you see that? And maybe it would be better if I did another color. I don't know. Let me try red. As my x values are approaching 2 from the left, my function values are approaching 3. Now, as my x values approach 2 from the right, watch this, folks, this is important. My function values are approaching, what is this? Approaching what? 1. I know that it's undefined here, it's an open circle, but it's you're really considering what are my function values approaching as x approaches 2 from the right, and my function values are approaching 1. Now wait a minute, these values are different, right? As x approaches 2 from the right, my function values are approaching 1. But when x approaches 2 from the left, the function values are approaching 3. So since the function approaches different values, I'm going to write this down. Since the function approaches different values depending on whether x approaches 2 from the left or from the right, we say the limit does not exist. So very important, okay? So go ahead and add that to your notes. Since f of x approaches different values, depending on whether x approaches 2 from the left or from the right, we say the limit does not exist, okay? Because it's not one particular value that your function value is approaching. This is an example of a limit that does not exist. Does not exist. I want to show you a couple more examples where the limit does not exist. Okay, we have the limit as x approaches 0 of this rational function 1 over x squared. Let's go ahead and get the graph of this function, and then we can determine the limit if it exists. Okay, this would be the graph, and you can plug in values if you'd like to get the graph, or just realize that this ratio will never be negative, because the denominator will always be positive. Regardless of what real number you plug in for x, x squared will always be positive, so this will always be a positive output, so the whole graph is above the x-axis. If you plug in 1 squared is 1, and 1 divided by 1 is 1, so it goes through 1, 1, right? It also goes through negative 1, positive 1, by the way. It will never touch the x-axis, because if it touched the x-axis, that means your y value is 0, and this will never be 0. The only way this could be 0 is if the numerator were 0, but the numerator is fixed at 1. So there's a horizontal asymptote right here on the x-axis. So these curves, these branches, will get infinitely close to the x-axis, but never touch it. There's also a vertical asymptote at x equal to 0. You cannot let x be 0 because then the function would be undefined. So there is a vertical asymptote all along the y-axis right here at x equal to 0. So these branches are getting infinitely close to the y-axis, but they're not allowed to touch it. All right, here we go, folks. The question that they want us to consider is, what is happening to your function values as x approaches 0? Well, as x approaches 0 from the left, your function values are approaching positive infinity. As your function values approach, as your x values approach 0 from the right, your function values approach positive infinity. So if you refer back to our definition for a limit, we said the limit, we called it L. Do you remember that? The limit had to be a real number. Infinity is not a real number. It has to be a finite real number, and infinity is not a real number. Therefore, we must conclude that the limit does not exist. All right, so make sure you have this in your notes, all right? Okay, the previous example showed us that the limit did not exist because the function values approached different values as x approached. Let's see, x was approaching, in the previous example, x was approaching, as x approached 2 from the left, as x approached 2 from the right, you had two different values that your function values were approaching. So the limit didn't exist. Here, the limit does not exist because your function values are growing very large, right? Arbitrarily large, going toward infinity. So, and the limit has to be a real number. So let me show you one more example of a limit that does not exist, and then we'll make some conclusions for our notes. Here we have a trig function. So it's the limit of sine of 1 over x as x approaches 0. What I propose we do is to create a table of values and then also look at the graph and make our conclusion there. All right? Now, as you make your table, you want to plug in some x values that are approaching 0 from the left. That would mean some negative values that are really small, right? And you also want to plug in some x values that are approaching 0 from the right. So some positive values coming from the right. Okay, I'm choosing these values here. You don't have to choose these particular ones, but I'm letting x approach 0 from the left. And so I'm choosing negative 0.1, then a little closer to 0, negative 0.01, a little closer to 0, negative 0.001. And then I'm going to approach 0 from the right. So I'm starting here at 0.1, a little closer to 0, 0.01, a little closer to 0.001. Let's plug each one of these values in for x and figure out what these function values are doing. So this is interesting. Notice that it seems to be jumping around a lot. I mean, we went from 0.544 negative 5.06, and then all of a sudden it goes negative 0.827, and then from the right we're at negative 5.44, negative 5.06, and then positive 8.27. So this is really, really interesting. What you might want to do is use a graphing calculator. You can always go to desmos.com, and punch this function, sine of 1 over x, into the graphing calculator there, and to get a graph going, okay? And you're going to find the following graph. Forgive my sloppy graph, but this is what you should be getting if you use a graphing calculator. Notice that the graph oscillates faster and faster as x approaches 0, right? It goes up, up, and then down, up, 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 right? So as you get closer and closer to 0, the function keeps on bouncing up and down very fast, right? So that kind of helps confirm our suspicion of these function values earlier when we were building our table. So when you really think about it, as x approaches 0 from the left, let me do this really quickly. As x approaches 0 from the left, and from the right, it seems like the function values can't make up their mind. Sometimes they're up here, then they're down here. So they do not approach a single unique value. They do not approach a single unique value. Therefore, we say this limit does not exist. All right, great. So add that to your notes. And now I would like to list some conditions under which the limit fails to exist. All right, and I want you to reference the last 3 examples that we just went through. All right, so here's our conclusion. All right, these are some conditions under which a limit fails to exist. So first, f of x, the function values, approaches a number L as x approaches a from the left and approaches a different number m as x approaches a from the right. This is describing what happened to us when we were dealing with that piecewise defined function a few minutes ago. From the left, the function values were approaching 3, while from the right, they were approaching 1. And so the limit failed to exist, right? The second condition is your function values become infinitely large in absolute value as x approaches a from either side. And so this was like the example we were graphing the rational function 1 over x squared, and the function values were approaching infinity. So the limit did not exist there either. Finally, when your function values oscillate infinitely many times between two fixed values as x approaches a. So this is an example or describing that trig function sine of 1 over x. And the function values couldn't like make up their mind, right? They were above the x-axis and below the x-axis, above the x-axis and below the x-axis, and then that happens more rapidly as you approached 0, remember? So the limit failed to exist. All right, make sure you have these in your notes. We will end this lesson here and then continue our study of limits in the following lessons.